Just quickly, the syllabus also refers to LED, LCD televisions, plasma televisions and 3D television. Let's just have a look at plasma first. It's superseded now by OLED, but the syllabus still asks that you know how it works. As you know, there's 4 states of matter. There's solid, liquid, gas. The 4th state is plasma, which is what's happening inside a fluorescent light. You put a positive and a negative charge across each part of a fluorescent light, each end of a fluorescent light. You've got a gas there in a near vacuum, and that energy physically, the electrical energy physically splits the atom apart into electrons and protons. That's a plasma. Plasma TVs did exactly the same thing. They had a neon light, so you had running down here, I'll pick a different colour other than blue. You had running down here, positive wires. You had running across here, the negative wires. If I connect this one and that one, then this would light up momentarily. Release a plasma. That plasma light released a UV ray, which then hit a red, green or a blue phosphorus. So this one might have been red, red, red. That one might have been green. This one might have been blue. So each individual dot was an individual cell, and when you excited the neon light or the plasma, it generated ultraviolet rays that lit up each pixel. The advantage in these was you got a perfect black, because if you turned off the electricity, no light came out and it was black. That's a great advantage for plasma televisions at the time. The disadvantage is they were really energy intensive, really power hungry. Cathode ray tubes were incredibly cheap. LCDs, LEDs were reasonable. LCDs were dear. LEDs are reasonably cheap to run. Cathode ray tubes were the cheapest, but unfortunately they're not high definition for this day and age. So that's how a plasma television worked. Let's have a look at an LED or an LCD. They are the same technology, just 2 different ways of generating the light at the back. Essentially, you've got either a bank of LEDs behind a television in an LED TV, or a fluorescent tubes once again, behind an LCD television in a box out the back. The tubes take up a lot more space than the LEDs, so LCD TVs are thicker. Then you've got a diffuser there to spread the light. Then you've got a polariser crossways. I'm going to put this in front of the screen in a sec, but these are polarising sheets. Right now they're 90 degrees apart, right now they're the same way. We're going to talk about polarised light. You've got the 2 sheets like that. That's about as good as black as you can get. As you can see, you can still see through it just. If I was to get my torch out, you could see the light coming through that. As you can see, even with the polarisers at 90 degrees, you can still see light coming through it. Obviously a lot more light. Let's see if it gets in focus. There it goes. A lot more light when it's here, but even at 90 degrees, you can still see the light coming through the sheets. So the problem with LCD LED TVs, is that you never really got a true black. OLED TVs, organic LEDs, are a bit better at producing a perfect black. So here we've got a polarising sheet with the polarising going horizontally. You've got a liquid crystal. I'm just about to talk what that does. You've got the polarising sheet vertically, so nothing goes through it. There's horizontally polarised, there's vertically polarised. And in front of that, you've physically got a coloured sheet with tiny dots of red, green and blue just basically printed on it. So you've got white light behind the screen. You've got over here, you control the voltage pixel by pixel going to these liquid crystals that control the light that comes through. So you control it pixel by pixel, and then if you want to light up all blue, you just basically turn on the liquid crystals behind all the blue dots and the light gets through. If you don't want any red or green, you just leave it so it's turning black. How liquid crystals work: liquid crystals rely on light and the fact that light, when it's being transmitted randomly, some of the waves are going up and down. Some of the waves, light waves, are travelling side to side. Some are at this angle, some are at that angle. So they're basically, if I was the light from my face to the video lens, is basically transmitting in every direction. Light, as you know, has a wavelength. The wavelength of visible light is around about 1/8 of the human hair. But it is basically something that you can measure, is its wavelength. If you make a series of gratings about that space, then the light will only pass through if it's physically aligned vertically. So if I've got the gratings vertically, the light only passes through vertically. Here's a polarising sheet. Right now, the light's getting through it. I'm going to put both sheets like that. As you can see, the light is travelling through both. It's coming through the first sheet that's closest to you. It's coming off my shoulder through the second sheet. Right now, these are two polarising sheets, and all the light that's coming through this first sheet up near my back shoulder is now travelling up and down. This polarising sheet has chopped out every light wave that was travelling horizontally. So right now you can see, if however this front sheet is also only allowing light that's going up and down to travel through it. So vertically aligned light both ways, if I turn that 90 degrees, this back sheet is only letting vertical light through, the front sheet is only letting horizontal light through. That's how light polarising works. Liquid crystals are basically a long chain compound that slowly twists when you put voltage on it. So if I put no voltage on a liquid crystal, that's how a liquid crystal sit inside a TV. I'll see if I can just sit that on my arm. Right now, this back sheet's letting through vertical light, the front sheet's only letting through horizontal light. If I was to somehow or other able to twist that light between the two sheets by applying voltage, I can control how much light gets through. That's what they do in an LCD screen. They've got the LCDs, or the control of these liquid crystals, down to pixel resolution. We'll have a look at a screen in a second, but just right now, just know that an LCD screen is basically bending the light between these two polarising sheets. The more voltage you apply to the liquid crystal, the more it bends the light. 0 voltage gives you that, full voltage gives you that and lets the light come through. Out the front of it, we just have a screen with red, green, blue dots on it that become your image. Right now, here's a screen. I've just got a magnifying app on my mobile phone so you can see the colour. As you can see, magenta is red and blue, green is just straight green, cyan is red and green, yellow, oddly enough, as you can see, yellow to your eye is actually red and green mixed together. White is all three. As you can see, it's just not, the phone's not focusing for a reason. There you go. And oddly enough, red is just turn on only the red pixels. Blue, black is turn on none of them. And as you can see, the bands of colour are actually a combination, like so.